Now let me briefly introduce myself. I'm Yao Cheng from Institute of Information Engineering, CS. It's my pleasure to give a speech about revisiting anonymity in post-quantum public key encryption. This work is cooperated with Xianghui Lu, Zi Li, and Bao Li. This presentation is divided into 3 parts: backgrounds, results, and the technical overview. Let us start with the background information. First, we introduce what anonymity is. Roughly speaking, anonymity means that a ciphertext conceals information about the public key used in its creation. As a comparison, let's first look at the security of indistinguishability, which is the standard security for PKE. In this security model, the challenger generated 1 pair public key and secret key, and a secret pair under this public key. Adversary will get the public key and the secret pair, where the key is the corresponding key with half probability and is the random key with half probability. But the adversary cannot distinguish between these 2 cases. And in the security of anonymity, the challenger generated 2 pair public key secret keys and generated a secret pair under one of each. The adversary cannot tell secret are generated from which public key. And roughly, indistinguishability guarantees the confidentiality of the shared keys, while the anonymity guarantees the confidentiality of identities, which goes beyond indistinguishability. And there are applications for anonymity, such as the cache anonymous credential system, auction protocols, and anonymous AKE, and so on. We focus on the design of anonymous PKE scam, and currently most efficient PKE scams are established based on FO transformations, such as mode summations in the NIST PQC standardization process. And FO transformations convert an PKE with weak security to a stronger one. And we focus on the performance of FO about anonymity in the QROM. Moving on to the next slide, let us review previous works. FO can be categorized into 2 cases. One generated CAMs with implicit rejection, where the decapsulation algorithm returns a random string for an invalid ciphertext, and the other generated CAMs with explicit rejection, where the decapsulation returns a rejection symbol for an invalid ciphertext. And ANOCC security is a stronger form of anonymity, which involves providing the adversary with decapsulation oracles. There are 2 main problems to prove ANOCC security of FO in the QROM. Proofs in the QROM considers the case where quantum adversaries exist and the adversary can access it with a superposition state, making the proof more difficult, especially the simulation of decapsulation oracles. For an implicit case, remapping technique in combination with domain separation technique is commonly employed to address the simulation of decapsulation oracles in QROM. Precisely 2 independent internal random oracles are required to simulate 2 decapsulation oracles, and imperfect simulation occurs if 2 decapsulation oracles need to respond with the same key. Such a case may occur because the ciphertext may be decrypted into the same message as the two secret keys. Graphs solve this problem by adding additional property named Clayton freshness, which roughly where the probability of generating the same shared key under two different secret keys is considered negligible. Later, Sagawa proposed a stronger security named SPR. This security involves one paired case in its security notions and implies anonymity. He proved that this security can be established based on SDS-IND security. Also, SDS security is stronger than weak anonymity, and for the explicit keys, the result is based on the Apple versions with an additional hash. And to the best of our knowledge, no previous work exists on the anonymity of CAN obtained from the textbook Apple Encryption. Now let us see the results. We revisit the anonymity of CANs obtained from Apple Encryption and the anonymity of hybrid encryption where the CAN them paradigm involves implicit and explicit cases. Opposed to the existing result of Apple, this paper weakens the security assumption for the implicit case and requires no additional hash for the explicit case. As opposed to the existing results of CAM and DEM, this paper refines the paradigm into the implicit and explicit keys to discuss respectively, making the conclusions much more clear. Now I'd like to move on to the technical overview. We adopt the modular analysis approach proposed by Wolfhans, and they decomposed Apple transformations into T transformation and U transformations. They proved that the IND-CC security of Apple, while we proved its NO-CC securities. Specifically, the transformation U converts a weak NO-CC-OA secure DPK to an NO-CC secure CAN in the implicit case. And the transformation U also converts weak NO-CC-OA secure DPK to a NO-CC secure CAN in the explicit case. And the transformation T converts a weak NOCP secure PK to a weak NOCC secure DPK. Here, CCOA secure means providing the adversary CCO oracle, and CCOA means providing one more oracle serial. And the CC security implies these two securities. And later we will introduce these oracles. CVO is utilized to ascertain the validity of the ciphertext, and CCO answers whether the plaintext and the two secret keys are the same. The difference between the implicit keys and the explicit keys is that in the explicit case, there is one more requirement to determine whether the decapsulation oracle outputs the rejection symbol, and the provision of a CVO oracle by the underlying PK can achieve this. Next, we explain the remapping technique to simulate decapsulation oracles in the QROM. For the valid ciphertext C, the encapsulated key equals HMC. To simulate the decapsulation oracle without the secret key, internal oracle from C to key is utilized to maintain consistency between the decapsulation oracle and the random oracle. Specifically, MC is the input of H, and also C is the input of the internal oracle HM, where C is generated PKM. And the output of H equals to that of HM. For anonymity, two public key secret key pairs need to be considered when simulating two decapsulation oracles by remapping technique with two independent internal random oracles. Such an issue will occur that the simulation is incorrect if the ciphertext is decrypted into the same message under two secret keys. And because H0C doesn't equal to H1C with non-negligible probability. And different from Graph's method of increasing the requirement of polynomial freshness, we mandate the underlying DP to provide CCO to detect this scenario. Consequently, the simulator responds with another identical dependent internal oracle for such ciphertext. This requirement naturally results in a finer domain separation for H. And that is the following four cases. In the previous part, we emphasized the necessity for the underlying GPK of the transformation U to be weak NOCCOA and weak NOCCOA is pure for the implicit keys and implicit keys respectively. Here, we demonstrate that the transformation T can achieve stronger security. Weak NOCC security. Conversely, CCO and CVO oracles can be simulated if one is accessible to the encryption oracles. In our result, the underlying PKE need to be Gauss-Brand. Formally, Gauss-Brand guarantees that adversary is hard to generate valid ciphertext C without querying the corresponding text M to the one oracle G. We can then simulate the one oracle G using the contrast oracle technique post-boundary, and subsequently we extract the correct plain text for a valid ciphertext using the online extractability technique. And that's all for my presentation. And thanks for your attention. Does anyone have a question?
Thank you very much. Are there any questions?
Hi, thanks for your talk. So I have a question. So according to your research results, so what is the anonymity we have about the like Kyber or maybe Frodo, classic Maker LAC etc. KM schemes?
Okay. The anonymity of these scams has been studied by maybe Sagawa and someone else. They have proved the anonymity of these scams, but they have additional properties. Maybe someone had the SF SCFR CPA security and Sagara needs the additional property of the SDS IMD security. These two security for us is additional, and we only require the demonstrand property. This is quite common and can be achieved by this.
Okay, thank you.
Thank you.
Are there any other questions?
Hi, thanks for your talk. So when I was looking at your results, I was a bit surprised that the implicit rejection variant also needs to require gamma spreadness. Is this just a proof artifact because you are using the extractable quantum random oracle model, or do you think that this additional requirement is actually meaningful because it has an impact on security?
I think the gamma spreadness is also needed in the implicit case, and as you see, we adopt the online expectability technique. If we don't have this property, maybe we cannot provide the CCO oracle for the underlying of the review test conditions. So I think
sorry. So I guess what you're saying is that the operators wouldn't commute nicely, right? So your proof wouldn't go through, but do you have a gut feeling whether there might be a proof that's maybe an alternative proof that gets rid of this additional requirement for implicit rejection?
I'm not sure about this. And in my opinion, in the implicit case, if we don't have this property, maybe we need.
Okay, so it's undetermined. Thank you.